All right, let me get the lights adjusted. Let's get started. So just so everybody's aware on housekeeping, homework 2 is due on Friday. It was due today, but I've gone ahead and posted homework number 3. Normally I'd push that one back as well, but at some point we kind of have to get caught up. Fortunately, homework number 3 is really short. Like, it's only 2 problems, and after today you'll be able to complete the entire assignment. So it's really short. I used to not even have an assignment on this, but I found that having a separate assignment on ACI requirements makes homework number 4, it makes the grades go up. Like, because generally what happens is if I have a separate assignment, like the idea is if I have a separate assignment on this, by the time you do homework 4, it's not like beam design and this. Like, you already are comfortable with this stuff. Before I did this, the homework 4 grades would be a little lower because it'd be a bunch of stuff that you had to do all at once. But again, this is a really short assignment. It's really quick. After today, you could probably do this assignment. You could probably do it in about 30 minutes. Like, it's real short. So today we're going to get into these ACI requirements, and maybe if we have time, we'll talk about how to design a beam. But before I do that, you all have a homework due on Friday, so are there any questions about that homework assignment? Have you started that homework assignment? I would hope. This is a little bit of a longer one, so there's like 5 problems on it. It's kind of big. So, any questions? Okay. Just remember, it's due Friday. No, already. Okay. Let me get this removed and see if I can flatten this out a bit. Okay. So last time, if you recall, what we were really focused on was trying to derive this, which is the fundamental stress block that we use in order to determine maximum moment capacity. And we had an example last time where we explored that. Sorry, get that out of your way. Did anybody have any questions on that example? Okay, now the thing about that example is it's great in order to determine maximum moment capacity, but that's not the only thing that we need to evaluate when we're assessing beams. So there's a couple different checks that we kind of need to perform. They're very minor and they're pretty straightforward, but we need to evaluate this in order to get a sort of an overarching picture of how the beam is performing. We also need to determine or discuss how to compute the resistance factor. Remember, the design methodology that we're utilizing is termed LRFD, load and resistance factor design. And so not only will you have load factors, things like 1.2 times the dead plus 1.6 times the live, but you'll have resistance factors. And so for beams, the resistance factor is something that you need to compute. So for those of you that are in steel design, the resistance factor is sort of just given. It's like phi is 0.9 or phi is 0.75. Whereas for reinforced concrete and for beams, it's really just for beams, but for beams and reinforced concrete design, phi actually changes. It depends on what's going on with your beam. So it's like, for those of you in steel design, what's the phi value for net section fracture? It's 0.75. What's the phi value for beams and reinforced concrete? It depends. It depends on what's going on with the beam. So we're going to talk about that today. Now, we went through some of these assumptions last time. So the idea that, for instance, that plane sections remain plane, we went through that. We have here, once we've determined where the centroid is, we assume that the strains vary linearly from the centroid or from the neutral axis. We also assume that the absolute maximum usable strain in the top of the beam is 0.003, okay? And that's just coming from looking at the stress strain curve for various different types of concrete and just sort of cutting it off, just sort of picking a point and saying, okay, that's our maximum usable strain. And so that value does not change dependent upon your type of concrete. It's always 0.003. So that's something to keep in mind. Okay? Now what does change is the depth of your is the ratio of the depth of your stress block to the depth of your neutral axis, and that's this term beta sub 1. We had this question last time. Remember, the term A and the term C are two different things, okay? So A is how deep your stress block is, from the top of the beam to the bottom of that stress block. And C is the distance to the neutral axis, so from the top of the beam to where there is 0 bending strain. So they're two different points. And the ratio between those two is beta sub 1, okay? Now, this is a point where students can get a little confused, so I really want you to pay attention, okay? This depth, from a depth of the stress block is always 0.85 FC prime, okay? It is always 0.85 FC prime. This depth, however, can change, beta 1 changes. And here's what I mean by that. If you look at beta 1 values, what happens is anytime that you have an FC prime that's 4 KSI or less, beta 1 is 0.85, okay? But as FC prime gets larger, beta 1 gets smaller. The idea is that as your FC prime goes up, as the concrete gets stronger, its ductility gets lower. It decreases in ductility. So for the sake of discussion, let's just make up a number. Let's say that FC prime is 6,000 PSI or 6 KSI. That means that beta 1 is 0.75, but this is still 0.85. This is constant, okay? So this value will always be 0.85. This value varies as a function of FC prime. So I'm telling you that now because I want you to be aware of that. If we're using 4 KSI concrete, they just happen to be both 0.85, okay? That's a great question. And so the question was, well, what if it's in between? The answer is yes, you would just interpolate. So this image over here on the left is sort of a graph of what you see here. So anywhere between 4 KSI and 8 KSI, it's linear. So if you had like 4,500, your beta 1 would be 0.825. That's a great question. So, but remember, the depth of that stress block is always 0.85 FC prime. That is constant. Everybody okay with that? Okay. All right. Here's another limit. ACI places a limit on the minimum amount of steel that you can put in a beam. Like basically what ACI is saying is, I don't care how much steel you actually need from a capacity standpoint, you have to at least provide that much, okay? Now in reality, in beam design, very rarely will you approach that limit. In other words, what will happen is you'll compute a minimum area of steel of, let's make up a number. Let's say you compute an AS-min of 1.2 square inches. That's what ACI is saying is the minimum, but you end up providing like 3 or 4 times that amount. And usually in design scenarios, this ends up not being that big of a deal, but you do still need to check it, okay? The reason why we have a minimum steel requirement is because it guards against sudden failure. Remember, if you don't have any rebar at all in a concrete beam at all, what will happen is you start loading it, and once you hit the modulus of rupture, it's gone. Cracks in half, and boom, it's done. Very sudden, very quick, it's done. So ACI says you got to at least put a little bit of steel in there to ensure that you're going to guard against that sudden failure happening. Remember, think about this. If we were in the building, if your grandma was in the building, if she was on one of these floor beams and the beams failed rather suddenly, grandma would not be having a good day, right? We don't want anything to happen to grandma. So we put at least a little bit of steel in the beam to guard against that sudden failure. Make sense? Now, a couple things. We see a square root of FC prime. Remember I told you you're going to see that a lot. You put in PSI, you get out PSI. So we compute our minimum steel requirement based on the following equation. We take this fraction times the maximum of either 200 PSI or 3 times the square root of FC prime, whatever's the maximum. The only other thing worth mentioning is this term B sub W, okay? B sub W is just, like here, B sub W is just the width of the beam, okay? The reason why there is a B sub W is because later on we'll have T-beams. We'll have a beam that looks like a big T. And so the width of the stem or the web is going to be B sub W, and then the top is going to have a width of B. So that's why there's a notation difference. But for rectangular beams, it's the same. Yes, sir?
So in that equation, that's in the bracket, you have the 3 square root of FC prime over 200 PSI. You're just going to multiply with whichever number is bigger?
Yes, the maximum of those two quantities. So if you compute this and it comes out to like 208, it'd be this fraction times 208. If you compute this and it's like 150, it's that times 200. So it's whichever's bigger. Yep. Great question. Any other questions? This is good stuff. All right. Now, let's go back to this. So remember, this is our strain profile, right? This is our strains. Remember, our strains are 0 at the neutral axis, and they vary linearly away from that. And then the very, very top of the beam, the region in compression, we have a strain value of 0.003, right? So if you recognize that, you could use similar triangles to figure out what the strain is here. Because think, 0.003 is to C as whatever this value is to D minus C. Make sense? So I could use that relationship in order to determine what is the strain in the tensile steel. So that term epsilon sub T, that is the strain in the tensile steel. Why do we care about computing that? Who cares? Like, why do we need that? If you recall, do you remember in our last example how we just said, we're just going to assume that the steel yields? Well, maybe we need to verify that assumption. We can verify that assumption by comparing that strain to the strain at yielding, right? Remember, what does a stress-strain curve look like for steel? Remember, it goes up, and then it plateaus and sort of goes off like that, right? And remember, that's the Young's modulus, right? And this right here, oh, I don't know what happened there. That's the yield stress. How would we determine what that is, the strain at yielding? Well, we take Fy and divide it by the Young's modulus, right? So it can tell us what the strain is at yielding, okay? We would then compare that to the strain that's actually in the beam to determine whether or not it actually has yielded, right? Because remember, we're assuming it yields. Let's determine whether or not it actually has. That makes sense? Now, we need the strain in the steel for a couple of things. Now, first off, ACI has a specified limit. They state flat out that the strain has to be greater than or equal to 0.004 in a beam, okay? So a beam, remember, beams are going to have regions in compression and regions in tension. This limit wouldn't apply if we were looking at something like, let's say, a column. Because a column, all you're doing is taking that column and you're squishing it. There is no region that's in tension in a column, right? But in a beam, you're going to have regions in compression and regions in tension. What the code says is that any beam or any element that has, really small amount of axial load, the strain in the steel has to be greater than or equal to 0.004. And so basically that's the code's way of saying that the steel has to yield, okay? The reason why the code wants the steel to yield is because they want the beam to behave in a ductile fashion, okay? So let's talk about ductility. Sorry. I don't think I'll ever get over this flu. My voice is going out. Okay, let's talk about ductility, all right? We have a term that I'm going to introduce right now, and the term is called a tension-controlled section. Now, a tension-controlled section, it's really just a fancy way of saying this, okay? You have a reinforced concrete beam, so you have concrete in compression, and you have steel in tension, right? A tension-controlled section is a section that's behavior is governed by the behavior of the steel. In other words, the steel yields before the concrete crushes, okay? Generally, we want that to happen, Okay? Steel is a very, very ductile material. So if you take a tension-controlled section and you start loading it and the steel yields first, what ends up happening in the lab is you have very, very large deflections. And there's a warning of failure. I mean, if you see a beam like this, you know to get the hell out of there, right? You know because it's obviously deflected, it's time to move. We want sections to be tension controlled. What we don't want is for a section to be compression controlled. A compression controlled section is where the opposite happens, where the concrete crushes before the steel yields. We don't like that to happen at all, because when that happens, what that means is there's very, very little warning of failure. You're loading the beam, the concrete crushes, bam, it's done. How many of you tested concrete cylinders before? What happens? You load, load, load. They can pop, right? They go boom. And looking at the cylinder, it's not like you were looking at it and you expected it. A lot of times it just goes, right? Especially the drier the cylinder, right? Well, think about a reinforced concrete beam. You wouldn't want that to happen to a beam, right? You wouldn't want the concrete to crush before the steel yields, because when it fails quick, okay? We call that a compression-controlled region. Now, a transition region is somewhere in between, and I'll sort of define that a little more rigorously as to what that means. But that's when the strain in the steel is somewhere between when it yields and 0.005. Again, at failure, we want the steel to have yielded like crazy. We want a lot of strain in that steel, because that's going to represent a more ductile section. So how do we handle this from a behavior standpoint? Well, that's where these strength reduction factors come into play. That's where these resistance factors, the phi values. Remember, phi values take into account uncertainty, not only in the behavior of the material, but the equations that we use, but it also tries to ensure a uniform level of safety, okay? And so here's sort of the idea behind a phi value. What we do is we look at the behavior of a beam and we say, okay, here's how the beam is going to behave. What is its resulting phi value? Let me ask you a question. Let's just make sure everybody's paying attention. Do we prefer that beams are tension controlled or compression controlled? Tension controlled. So let's say I had a beam that was tension controlled and a beam that's compression controlled. If I had a beam that was compression controlled, that would represent a more dangerous beam, right? So as a result, do you think my resistance factor, like should I be more conservative with a compression controlled beam or less conservative? I want to be more conservative, right? All right, look at your phi values. Okay, so what I have here is a graph, and on the x-axis, what we're looking at is the strain in the steel. Okay, so as the strain in the steel gets larger and larger and larger, so as the strain in the steel goes up, the phi value goes up. Okay, so we start off with a really, really low phi value, and then it creeps up, and then it gets to a really high value. Okay, what we end up doing, remember that MN value that we computed last time? We take that MN value and we multiply it by phi. So if we have a tension-controlled section, we would multiply it by 0.9. If we have a compression-controlled section, we multiply it by 0.65. Think about what that means. If the section is compression-controlled, that's a more inherent level of danger. So we're reducing that usable capacity more. We're multiplying it by 0.65. Whereas if it's tension-controlled, we say, well, that's more along the lines of what we want, and so we multiply by 0.9. Does that kind of make sense? Yes.
One thing is when designing a beam, how do you know whether to use compression or tension control before the beam is like?
That's a great question.
That's kind of what I was going to ask. Compression control is like just throwing steel in there, or tension control is like applying tension to the steel as the concrete.
You're both sort of like right on the same page. Let me say a couple things about that. First off, in design, you don't have a clue whether the beam's going to be tension controlled, compression controlled, because you're in design, right? You haven't proportioned the beam because there's no beam, right? So what that means is that you have to make an assumption. Now, in design, we desire tension-controlled behavior. So in design mode, we make an initial assumption that the beam is tension-controlled. But it's an assumption. So in our design process, we have to go back and we have to check and make sure that assumption is valid. Okay? And it's possible that it isn't. Okay? Now what you were saying, that's a very astute observation. In fact, in reinforced concrete design, the more steel that you throw into it, see, you kind of got, if you really have an understanding of C equals T, of compression equals tension, the more steel, the more reinforcement that you just throw into the beam, the more you are demanding of the concrete. So what ends up happening is a lot of people think, well, here's my beam. I'm just going to throw a few pieces of rebar in there, a few extra pieces of rebar for good measure. You know, make me feel all warm and fuzzy at night. Well, by throwing all that extra steel in there, you might actually be causing the beam to go from, let's say, a tension-controlled region to a transition region. So your phi value could go down, and the beam's actually not as strong as you thought. So you got to be careful about that. And we're going to talk about that when we get into design. Okay? Now, let me ask you a question. What type of reinforced concrete element in buildings do you think is always going to be compression controlled? Well, we can't avoid it. Foundation or columns. We're talking about elements being squished on. So when we do column design, our phi value is going to be 0.65 every time. Except for if we've got circular columns, we're able to bump it up a bit. So for circular columns, we end up using 0.75. But the reason why is because we use a different type of confining reinforcement that makes the column behave a little better. So, everybody good? Yes.
You have a compression control beam.
Yes.
And the concrete compressions.
Yes.
The steel yield.
Yes.
How does the steel just completely irrelevant at that point?
There's no beam.
Okay.
So,
why does the steel, I guess, have to yield? Like, how does that help it? I'm not seeing that.
because okay, so here's the thing about steel. Steel is a material that is very, very ductile. It can withstand deflections far beyond yielding. Okay, so do you remember? I don't know if I showed you all in this class, but I think I showed you in steel design. Do you remember me talking about the football field analogy? How up until yielding, that's basically the 1 yard line, and then everything past that's the rest of the field. Steel has a remarkable ability to withstand deflections far beyond yielding. So if you're loading, let's say, a beam, and the steel yields first, it's going to stretch like crazy. And so instead of the beam like crushing and failing and failing miserably, it's going to gradually and slowly deflect, but it's going to show a large amount of deflection before failure. So we as the user are going to be able to see that. So put yourself in the user standpoint. Would you prefer, if a beam's getting ready to fail, would you prefer to see the beam like this so you know to get the hell out of the way? Or would you prefer to just be standing there one day and boom? So that's why we prefer tension-controlled regions, or tension-controlled sections, sorry.
So the tension control section, that would make the steel want to deform before the concrete.
Yes, yes.
Instead of the concrete just giving in, the steel's going to get first.
Exactly. And so you've got a lot of warning before failure. I mean, there's a point, like once you hit 0.85 FC prime, you're stress blocking the concrete, and FY in the steel, the beam's gone. But at least you knew it. At least you knew it was coming. This is good stuff. This is really good stuff. Any questions?
Do you ever have a situation where you have steel on top of the wall?
Yes, absolutely. In fact, that's called a doubly reinforced beam. And in fact, in doubly reinforced beam analysis, the question that we have to ask is, does the compression steel yield? Because sometimes it does, sometimes it doesn't. Now, we include compression steel for a few reasons. First off, as we'll see later, you get a bump on long-term deflection performance. If you include compression steel, you actually improve your long-term deflections. So that's one reason to include compression steel. Another reason to include compression steel in your analysis is because more often than not, it's there anyways. Okay? When you have a reinforced concrete beam, there's more than just the rebar at the bottom. We're going to talk later on about shear design and how there's stirrups going along the beam. So here's the beam, you got rebar at the bottom, and you've got all these stirrups going along the span Usually you end up putting a couple bars up top just to tie everything together. So more often than not, that compression steel is there anyways. So you might as well count on it. Okay? Now, analytically, we have to determine whether or not that steel yields, but we'll get there. That's something we'll do later. Like once we do rectangular beams, which is what we're doing now, we'll do T-beams, then we'll do doubly reinforced sections. This is good stuff. Any other questions? This is good stuff. All right. A couple notes regarding notation, and I've been trying to be clear on that. And this was asked, I think, about one of the problems on the homework. Just so you are aware, D is the distance from the top of the beam to basically the centroid to where the steel is. So if you only have one layer of steel, it's just right where the steel is. But if you have two layers of steel, like you do here, then D is to the center. Whereas this limit here on epsilon sub t and this limit here on epsilon sub t, what we're talking about is the strain in the lower region. This is only relevant if you have two layers of steel. More often than not, in regular old building design, you can probably get away with just using one layer. You know, use bigger bars and use fewer of them. Excuse me. Well, in bridges, there's a well, don't think that way. Just starting to throw rebar in there. Let me say this. You have probably in your research in senior design come up or seen the term pre-stressed. How many of you have heard the term pre-stress? Okay, so here's how pre-stress works. Concrete is a material that behaves very poorly in what? Tension. Okay, so here's how pre-stressed concrete works. Imagine I have a piece of PVC pipe right here, piece of PVC pipe. And let's say I feed a rubber band through it. Okay? I got a rubber band in the middle of a piece of PVC pipe. Okay, and I use some binder clips on each end. I take that rubber band and I stretch it like crazy. And then I use some binder clips to sort of lock that rubber band in its stretched phase. So the rubber band is experiencing what? Tension or compression? The rubber band's being yanked on. But what happens to the binder clips? Like I've got this pipe, stretch it, binder clip, and I let go of the binder clips. What happened? They snap to the ends of the PVC pipe. So what's the PVC pipe experiencing? Compression. The way pre-stressed concrete works is we take these super high strength steel cables, run them through a concrete beam, and apply a bunch of tension. And we lock that tension into the cables. What does that do to the beam? It locks in some compression. So here's the idea. Concrete is a material that behaves very poorly in tension. So in the regions that it's experiencing tension, put some compression in there. Lock in a compressive force that'll negate that tension. That's what pre-stressed concrete is. And so you can get away with using like a thinner beam and less concrete, and the beams, they perform a lot better. Like they can achieve spans that they wouldn't be able to without pre-stressing. Now, to be clear, pre-stressed concrete is something we might talk about near the end of the semester. The math is a little more difficult. The reason I mentioned pre-stressed concrete is if you look at bridge girders, if you're talking about something like 100 feet, 120 feet, you can see like a girder, and it has a pattern of like 30, 40 different strands at the bottom, and it's like a big grid of cables that are meant to lock in that compression. So, but that's a whole nother animal. So, it's a little more difficult. There's stress limits and all sort of stuff.
They also apply vertical.
What's that?
They also apply vertical loads with the pre-stressing.
Not really. Actually, it's usually just like here's the beam, and you run the cable in the tensile region. That's usually what you do. Now, if you have a post-tension section, you can run the cables in like a parabolic fashion that can sort of counteract the moment diagram. But I mean, we're getting we're getting into some areas. I can talk about this stuff all day. Any other questions? All right, what I want to do is this. I want to take the problem that we looked at last time, and I want to go through these ACI limit checks. Very simple, very straightforward, but I want to go through this so that we're all clear on what's going on. Sound good? Now, okay, so here's the beam. Now, help me out before we move on or go into this. Can anybody tell me what A was? Because this is the exact same beam in the previous example. So what was A? 4.165 inches. And what was MN? Okay, sound good? All right. Now, first thing that we're going to do is we're going to utilize this relationship. A equals beta 1C. And we're going to solve for C. So that's going to be 4.165 divided by what? Now, what is beta 1 going to be for this problem? What was the FC prime? Anybody remember? 4,000 psi. So if FC prime is 4,000, what's beta 1? It's 0.85. Okay. Don't confuse that with the depth of the stress block, though. That's just coincidence. And so, what does this come out to be? Excuse me. 4.900 inches, right? Now, here's the thing. Here's why we needed that. We have a beam. We have some steel. We have a strain profile that looks something like that. Man, that's horrible. Right? So this dimension right here is C. Anybody know what this dimension is? Anybody remember? There we go. D minus C. And then what is this strain value up top? Anybody remember that? What's it always for every concrete? 0.003. So what we can do is we can use similar triangles to solve for that strain in that lower region of steel. Remember, 0.003 is to C as whatever that strain value at the bottom is to D minus C. Okay? So that's going to be epsilon sub T is 0.003. That's going to be 23 inches. Excuse me. That's 4.9. 4.9. And what is that come out to be? Let's scroll down a bit. .011. Do I have a second on that? Okay. Now, we can make a number of observations based off that value. Okay, first off, right off to the side, we can determine the strain in the steel at yielding. And so that's 60 KSI over what's the E value for steel? There we go. Burned into the back of your memory. And so what does that come out to be? .00 and it's 207, something like that, right? Okay. Okay. So from this, I propose that we can make 3 observations, 3 very, very important observations. First off, compare these two. What behavioral observation can you make? It's already yielded, right? Remember, we assumed that the steel yielded, right? We assumed that it reached Fy. Well, look, this is the strain at yielding, and this is what it actually experienced. That's like 5 times, right? So the assumption that the steel yielded, that was valid. So here, let me drag this down a bit. That was valid. Here's my second observation. What is the minimum limit? Let's see if you were paying attention. What's the minimum strain in the steel that ACI permits? 0.004. So what's the second observation that I can make? ACI requirement was met. In other words, that the strain in the steel is greater than or equal to 0.004. So that's been met. What is the third observation that I can make? Let's go back to tension controlled versus compression controlled. Tell you what, I will help you out with that observation by pulling this up. What observation can we make about the beam by looking at that? Is it a transition beam? Is it compression control? What's the deal? Tell you what, when do we start becoming a tension controlled beam? At 0.005. And what is our strain? 0.01. So you tell me, is this a compression controlled beam? What's the transition? What's the deal? This is a tension controlled beam. And if you have a tension controlled beam, what does that mean? Say it again. Phi is 0.9. There you go. So there's our 3 observations that we can make. Now, what if our strain was between these 2 values? Like, what if our strain was 0.0043? It'd be a transition region. We would meet the strain limit, but what would our phi value be? We'd have to interpolate, right? We'd have to use this. So So for beams, if our strain is between like 0.004 and 0.005, we have to interpolate, and we have to interpolate using that equation, okay? So we'll need the strain in the steel and then the strain at yielding, and this is just the equation of that line, so it's pretty straightforward. Yes?
So is this that, they set the requirement as 0.004, because they can't be controlled, it's like above that.
The 0.004 limit is intended to ensure that the steel yields. And ACI does set that limit. Yes, you are correct. Now, if you have a beam that has a strain between 0.004 and 0.005, ACI says that that is classified as a transition region, and so your phi value is not 0.9, you interpolate. And so this is just the equation of that line, y equals mx plus b. No. Okay. So what was epsilon sub y? We just computed it. It's like 0.002. So that would be when a compression-controlled region starts. But if the strain was below yielding. But let's be clear, in beams, that'll pretty much never happen. But it will happen in columns. Because in columns, in fact, you don't have a positive strain. You have a negative strain. Because the column is not experiencing tension, it's experiencing compression. Does that make sense? This is important stuff. I really want this to be clear. Sound good? Okay. So if you want, you can go ahead and say, therefore, phi mn is 0.9 times, what was it, 246.8? And so what does that equal? So just so everybody's clear as to what that number means, that's the number that we would then compare with 1.2 times the dead plus 1.6 times the live to see whether or not the beam is safe. Because what this number is, this is the maximum capacity of the beam adjusted by phi. Okay? So this is the maximum capacity of the beam, but reduced to account for those uncertainties and trying to ensure uniform safety. So you wouldn't compare Mn against your 1.2 dead and 1.6 live. You'd compare phi Mn. Because think, the 1.2 dead and the 1.6, those are your load factors. This is your resistance factor. So these are essentially your factors of safety, if you will, but it's a little more refined. So. You mean like if the resistances are less than your loads? That means that your beam is inadequate and you need to redesign it. That's exactly what that means. And what we're going to do next is discuss the process of how do you proportion a beam so that that doesn't happen. And that is reinforced concrete design. Just like in steel design, the idea is to select members that can safely resist the load. It's the same thing here. Just the math and the mechanics are way different.
So a normal moment that we calculated last time is like the absolute that would be
The absolute, yes.
This is what we have to look at when we're designing, so that we're not even close to what it's.
Exactly. Because keep in mind, not only are we reducing the capacity, but we're also at the same time increasing the loads. Remember, we take the dead loads and we multiply them by 1.2. We take the live loads and we multiply them by 1.6. Why do we do that? Well, it's to ensure uniform safety. We up the live loads more because we're less certain about them. This is good stuff. Yes. This phi value encompasses things like uncertainties in your materials, uncertainty in the construction process. Who do you think builds these beams? People. We're not robots, you know. Uncertainties in our math. I mean, we're making assumptions, like 0.85 FC prime, that's an assumption. That's a mathematical model that might be off, you know. It's not that much off, but it's, you know, all those little uncertainties, that's what Phi is trying to take into account. This is good stuff. Everybody good? There is only one other thing that we need to do, and we need to check the limit on the steel, okay? So we need to check the minimum steel reinforcement. So here's what I'm going to do. All right, we have BW, which is B, and what was that for this beam? 10 inches. And D was 23 inches. Now what I'm going to do is over here off to the side, I'm going to compute 3 square root of FC prime. So that's 3 times the square root of, I do that right? No. What do? There you go. You put in PSI and you get out PSI. Make sure y'all paying attention. And so what is that? 189.7. All right, do I have a second on that? So what value do we use, the 189 or the 200? 200. So therefore, our AS min is BWD over FY times 200 PSI. So you're going to just pay attention here. So up top, we have 10 inches, 23 inches, 200 PSI. What do I put on the bottom? I know what is F sub Y. There you go. It's not 60 KSI, it's 60,000 PSI. See, this is why you write your units out. So chug that out and tell me what you get. 0.77 square inches. Do I have a second on that? Now, that is the minimum amount of steel that we have to put in the beam. How much did we actually put in the beam? 2.36. Yes, going back to the formula. Yeah, here's our formula that we're using. So it's the maximum of whatever this is in 200. And how did I get the actual steel? That comes from just the beam. It's 3 number 8s. So 3 number 8s has an area of steel of 2.36 square inches. So did we meet this limit? Yeah, we did. So therefore, min steel limit met. Yes. Well, I think that'll become clear next time when we discuss design methods, because we're going to tailor our design methods using some rules of thumb and then trying to avoid that. But what ends up happening is this, is that we end up calculating how much steel that we need, and then we pick the next iteration above that, but not too much. Like, for instance, there's only so many different patterns of steel. Like, you could use 4 number 9s, or you could use 3 number 11s, or whatnot. And so you calculate how much you need, and then you pick the next, whatever multiple of bars will be just over that. Does that make sense? Don't worry, we're gonna explore that. So, anything else? Yes. No, that's what homework 3 is for. So no, I just want MN. for homework 2. Sound good? These folks are excited for steel design, let me tell you. That's all I got, everybody.